So, welcome to the third video of this particular challenge. And this is pretty much a different sort of challenge that we'll be approaching dynamic programming. This is a lead code challenge called House Robber Challenge. You'll find the link right below as to where you can find the full description on LeetCode. So let's go ahead and get started. Let us understand what the challenge wants us to do. So first, it tells us that you're a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed, and we'll look at it. But the big problem here, and that's the constraint we'll be working with, is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into in the same night. So if we were to try organize a heist for the money stashed in all these different houses, the one constraint we have is we cannot steal from two adjacent houses. But what this wants us to find out is the maximum amount of money you can rob tonight without alerting the police. So, in simpler terms, we're going to have an array of numbers, which is going to be the amount of money that we can steal from different houses. And we're trying to maximize the amount of money we can collect, but we cannot steal from two adjacent houses. Let's look at those sort of example test cases and what this looks like. In the first instance, we have four houses. The first house has one. Second house, the value of money we can steal there is two. Third house is three, and then the fourth house is one again. Just eyeballing this, what we can do is we can steal from house number one, skip two, steal from house number three, and so that in total gives us four. Or we can steal from house number two and house number four, and that in total will give us three. So the optimal way for us to steal from these houses is to steal from house number one and house number three, where we get the output. So the maximum we're supposed to get with our code is supposed to be four in this sort of instance. So that's worth noting. Now let's look at a second test case in this scenario as well. Now we have slightly more houses, and you can see the value there. And the optimal sort of amount we should get here is we either steal 2 plus 9 plus 1, or we steal from 7 and 3. 7 and 3 gives you 10. 2 plus 9 plus 1 should give you 12. And you can see that's the ideal output you're supposed to get. But let's look at one other test case that's slightly different. And I know this is not a test case that's given on the lead code challenge, but it should be a test case over there. And that's going to be, what if we have an instance where we have house number one has two, and then we have one, one, and then two? What's the maximum here? We can either steal from house number one and house number three to get three, or from house number two and house number four to get three as well. But let's face it, if we steal from house number four or number one and skip the two houses and steal from house number four, the police system will not be alerted, and we'll still be able to get like the full amount that we need here, right? That's the maximum actually. So I'd go ahead and argue that um, you should not steal from adjacent houses, which is okay, but not stealing from adjacent houses does not mean you should always keep one. And this is a good example of where like skipping two houses gives you a better maximum than just keeping one house in that sort of regard. So the output here should also be four. That's actually the maximum amount we can steal from that particular chain. And that's like one test case that's not given that is worth noting for all the sort of solutions we'll be trying to come up with. Okay, so now let's get to understand how we're going to approach this using the top-down dynamic programming approach. I'm just trying to eyeball this for you guys so that you can be able to visualize how the code is going to be working. So imagine you have these six houses, and you're trying to maximize the amount you're going to steal from these houses. So from a top-down approach, we usually start from the end here, and we're just trying to say there's two ways for us to steal here, and I want us to really focus on finding the repetitive sub-problem that we're going to get off of here. And this is how to go about it. So the first option is we can either steal from the sort of the house, the sort of series of houses before the previous house. So if we're at this final house, I cannot steal from this house. So I can only steal from these set of houses. So yeah, so it's going to be that set of houses plus what I can steal from that particular house. So in real sense, the dynamic programming solution here is at this particular point, this is the final house, I have to skip the previous house and I have to maximize what I can steal from all the previous houses, skipping the previous house plus what I can steal on this particular house. So that's my first option. That's going to be my option A. And my option B is going to be what I can steal from up to the previous house without including the house I'm on. So that's going to be option B. And I hope you guys are eyeballing this extremely well. My first option is to maximize what I can get from this square or rectangle of mine. So what is the maximum I get there plus the amount I can steal from the final house? Or my second alternative is to just go ahead and steal from what is the maximum I can get from all the houses up to the previous one if I'm not stealing from the current house. So those are the two options. And what our code will be trying to do is it's going to try maximize between option A and option B, what's going to give me the maximum amount I'm going to steal. And this there is the repetitive sub problem because when you come to this sort of subset, let's say when you look at A, right, it's going to try get the maximum from house 2 where we have 2739 plus what we get from this final house, which is 1, and then compare it to the maximum of what we can get till there. And you can see that with the green box. But what you're saying is we'll call that recursive function, and that recursive function, whenever we try maximize what we can get from these four houses, it's still going to operate in the same way. So this is where the repetitive sub problem works out, right? Where even at this particular point, right? So if we take option A, so the function is going to call for us to look at the red box at the top here, which is what I've summarized down here. And when you're in that particular option, you will be able to get a new option A, which is, can I steal from this final house, skip the previous one, and the maximum I can get from these two houses. And I have to compare that from option B, which is what can I steal up to the previous house if I didn't include the final house as well. And I'm also trying to maximize these particular options. The moment you can visualize this, you realize that this loop can continue if you're working with a recursive function until you only have like an array of one sort of house or two houses, which is what you're going to handle with the if cases here. But this should be how you think about this particular solution. Now, most of you might be asking, how do does this really work out for when we need to skip two houses? And I want us to look at that like particularly here. So this is a good example of where we have to skip two houses for us to maximize the amount we can steal there. So how does this work? Let's look at it practically. So option A is we steal from this final house plus the maximum we can get from these two houses. So we are skipping the previous one there. So this will be 2 plus the maximum we can get from these two houses will be the maximum we can get from either house 1 or house 2. So that's going to be 2, right? So this is going to give us 2, which is the maximum we can steal from these two houses plus 2 there. So that actually gives us 4 versus what is the maximum we can steal from option B? In option B, we can only steal 2 plus 1, which is 3. So you can see even in this test case, if we apply the same logic we applied previously, it will allow us to skip two houses because this already smallest test case already fulfills that. And you can see the maximum is going to come from option A, which is going to be 2 plus the maximum we can steal from these two houses, which was still 2 because we are going to have this sort of like we're going to run the function by itself on those two houses, and we're going to look at the maximum, which is going to be position 0 versus position 1, which is still going to give us 2 as the maximum there. So it's going to give us 4. So worth noting that that sort of recursion works even in this test case where we actually have to skip two houses because we've just implemented the logic in the cleanest way possible. Now, most of these problems are usually harder to visualize first before you kind of get in code. So we should be done with the hard part. But now is how do we get it in actual code? And that's what we'll be trying to do right now that we've understood each and every single thing. So let's go to our Python code and let's see how we can go about it. So just to get us started, I just had to go ahead and set up the two test cases that we are working with and just understand like what the final sort of answer should be. So in this first one, we should get like 2 plus 9 plus 1. That should be the maximum at 12 instead of 7 plus 3, which is 10. And then in the second test case, we have two, we should get that sort of four, which is the instance where we're able to skip two houses and so get sort of thing. So once again, this is going to be a top-down approach. Note that I do not like a top-down approach for this particular solution, and you'll see why when we do the bottom-up approach in the next video. But nevertheless, this is going to be probably the smoothest one to understand because the recursion is very, very clear. So whenever I have a list of houses here with the amount of money I can steal from any one of those houses, what I'm really trying to do is I'm trying to return a maximum between those sort of two options. And the first option is, what if I stole from the final house, which is going to be nums minus 1. So the index for the final house should be minus 1, plus what I can steal from all the other houses ignoring the previous one. And once again, I'll tend to come back to this sort of thing. So when we look at option A, I want to steal from these houses up to this particular point. So I need to skip this previous one and then add the maximum of what I can get there to what I can get in this particular final house. So that's what you're trying to implement there. So it's going to be the final house value plus it's still going to be the same function, which is going to be what we can rob from all these houses. So that's nums up to -2. And you'll realize that when you run like this, so this is supposed to be a slicer. So you realize that when you do nums up to -2, when we have this particular array, it will give us this sort of subarray of 2, 7, 3, 9, right? That's going to be that up to -2, right? So that's going to be the first option. So the first option is we do this sort of sub array plus what we can get from the final house. So we're trying to maximize. So I'm not even trying to compute here. Let the recursion handle itself. So that's what that's what that function is going to give us. And then this is going to be the first option. And then option B, so I'll put a comma there. And option B for us is going to be what we can rob from all the previous houses, including when we don't include the house we are on. Once again, I'll come back to my visualization here. So that was option A. And option B is just what I can get from this entire subarray, right? And what I can get from that subarray is going to be still the same function. And then it's going to be nums. And the subarray is going to be up to that sort of -1. So when you run this, you realize that it will give us this particular subarray that we have there. So the green one there. And those are the two options that we're trying to do here. So it's like, what can we, it's like, what can we steal up to the previous house versus what can we steal up to the house before the previous one plus what we can steal in the current house you're on. Once again, it's very hard to say this in words, but I hope you guys understand it from that particular visualization. But this is what this code is going to do for us. But once again, just like the previous ones, you still have to understand that because at house number 1 and house number, when our array has length 1 and when our array has length 2, we don't have two previous subarrays. So go ahead and see this. We cannot be able to do up to -2 when we only have 2 and 7 or when we only have 2. So we have to have if cases for that. So go ahead and say that if length of nums is equal to 1, this is very easy. What we'll do is we'll just return that sort of 1 value in our array. So that's if we have an array of length 1. However, if we have an array of length 2, right? Once again, we still can't run that sort of recursion on this. So if the length there is equal to 2, then what you're going to do here is you're going to return nums, and then what you want to do is you want to return the maximum of the 2 items in that sort of array. So that's going to be maximum of what we have at index 0 versus what we have at index 1, right? That's well said. So this is the bottom-up approach. We have the two test. We have just the clear recursion here. So and you can see like we recall the function once again, makes our life extremely easy. And then on the final one we add this plus that, and we're trying to maximize. So keep in mind what you're trying to do in this sort of subset is we're really trying to maximize what sort of option should we go for between option A and option B. I hope that's very, very clear. Now, while this works very, very well, once again, it's worth noting this is just pure recursion. It's not dynamic programming yet because in a top-down approach, you need to implement memoization. But let's go ahead and see whether this works with the two options we have. So the first one, you should get 12. The second one, you should get 4. Let's see if that works. These are small arrays. You should be able to do that sort of recursion without any problem. So yes, we actually do get 12 and 4, so it's working very well. The only caveat here is we cannot really push this code to really, really long arrays because it's inefficient. Anytime we call the recursive function, it's going to compute things twice. So we are definitely going to have a chain similar to what we saw in the previous one, because some of these subarrays will be equal. Like when you go to option B and you run the functions again, you'll find a subarray that still is similar to the red one that we had in option A as well. And I don't want to repeat the entire tree we went through last time, but I think you guys were able to see that when you have recursion, there's a lot of repetition of functions or like recomputation of functions that happens under the boat there that you really want to avoid for you to make this efficient. And you'll start feeling it when the length of nums is extremely high. So to be able to solve for this, we need to go ahead and add memoization. Now, memoization for this top-down approach is going to be slightly different from what we saw with the Fibonacci numbers. With the Fibonacci numbers, we had a clear nth term, and in that sort of clear nth term, that would be our dictionary key, and then we'd be able to get the final value. In this one, we have to be slightly creative because we can't have a list as a dictionary key. So let's think about it. What would work well for us? I don't think this is the most efficient way, but probably in my mind, we could probably go for the length of the array. Because when we have like a clear array defined for us here called nums, right, we know the different subfunctions will be working with different lengths of array. So that sort of length could be a unique factor that we have within our particular function. So I'll go ahead and say that what we'll use as our keys, because we can't use a list as a key, is to go ahead and say that the length is what we'll be looking at. So length of nums is what we'll be adding to the dictionary. So what I want to do is I want to add a dictionary here, and I want to go ahead and say that if length of nums is going to be in our cache dot keys. So the length is what I'm going to use as the key here, because I can't use the full list as a key. So again, I need to make sure I add the dictionary out here. So cache, this will always be a dictionary. So cache here, this will always be a dictionary for me at the top there. And then now I want to go ahead and say that because I don't want to recompute things I've already computed, I'll just go ahead and say that if this sort of key, which is going to be the length of my array, is in my dictionary already, then go ahead and return what that dictionary tells me. So it's going to return the cache length of nums. So that's what you're looking at. So we are good, but then we always say that you always need to add you need to add new computations to the dictionary if they've not yet been added. So instead of returning here immediately, let's just go ahead and say our result is equal to that. So if it's already there, it will return here. So it won't get to this particular front. But if it does get to this particular front, we will compute the result. And then after that, we'll go ahead and understand that our cache, so we need to add it to the dictionary. So our cache length of nums should be equal to the result that we go ahead and output there. And then finally, we can return the result. Okay, so that's going to be our approach there. Our function was already working so well with the recursion, but now we've gone ahead and implemented memoization here. This is dynamic programming. We're trying to avoid repetitive sort of functions being called. We're trying to optimize the efficiency and speed of this particular code, and memoization is the easy way for us to go for it. Unlike the Fibonacci problem, where it was very easy for us to just have a simple dictionary out there, here we had to be creative and use the length of nums as the sort of dictionary key there, but it shouldn't be a problem. Now, because I've added a cache here on the dictionary, I also need to make sure that in the recalled functions here that we also have the second parameter cache. Okay, so that's going to be cache, so that we are starting from the already pre-existing dictionary there. Okay, so this is fine. We are good to go. Now let's go ahead and see if this is going to work just as well as the previous one. It should work faster, that's what we expect. We still expect to get 12 and 4 like we got here, So let's just go ahead and see this. I'll go ahead and run the code. And unfortunately, I get 12 and 11. Now, let's try debug to understand why are we still getting 11 for the second one. That's what's bugging us, right? We just got the right answers with the previous ones. I will just implement print statements here to understand where the problem comes from. Uh, I'll probably implement print statements just before I return to see what is the result it returns here and what are the nums that it is working with when we're there. So that will allow us to debug this particular code to understand exactly where the problem is coming from. Okay, so I'll run that and I see where the problem is coming from. So with the first one, it starts with the sub array of 279, right? Of course, when it's just 27, it's going to be automatic. It tells us the maximum there is 11. It goes to this other sub array, the maximum there is 11. And then this is the final one, and then it gets the maximum as 12, which is good, works well. But I see for the second sort of arrays, it just doesn't print, right? It feels like I get my end result 12, and then the other one, it just goes ahead and gets my end result. And I think I know where the problem is. Because our dictionary key is length, it does feel like in this sort of functions, we are using the previous cache. Like it's the same dictionary being pushed to the other one. Because you could see here, when length was equal to 4, so at this particular front, we got 11. So it meant here, it just went to the dictionary, got that 4, and outputted 11. So I think here we need to be creative and we need to go ahead and say that for this sort of function of ours to run well, we should always have our second entry, which is going to be cache is equals to dictionary for that as well. And I think that should be the case here. This is why I don't like this sort of top-down approach on this one. If it was a bottom-up approach, we would not have to worry about some small issues like this, because I don't think you want to be defining a dictionary each and every single time. You just want it to be automatic because you had already defined an empty dictionary. But you actually need to do so that you always start from an empty dictionary whenever you're running this particular code. So let's see if my assumption here, or it's a very well-informed assumption from what I can see here, is going to work. That is what I feel could be the test case. Let's see whether that's going to work. Yes, it does work well now. You can see the print statements work, and you can see now we initialize a new dictionary, and then I get 4 as well. So I was right in regards to that. If you didn't understand it, you can just simply just play around here. But anyways, what we're just trying to say here is if you don't define an empty dictionary here, it will start off from any other dictionary already called cache that's already existing in your memory. Okay, so now without the print statement, let's see if we're able to get the two results, so 12 and 4. So again, the reason I was able to know it has to be a dictionary problem is because our function used to work very well before memorization. So that's how we're able to debug that. So still, our function works so well. So that was 12 and 4. Now with memorization implemented, which means this is way more efficient whenever we are thinking about longer arrays of nums. But the only problem with memorization is we've optimized the runtime complexity, but you haven't optimized the space or memory complexity there. But this should now run with a runtime complexity of big O of n instead of big O of 2 to power n, because once again, we are always doing maximums of two functions, so it's always going to double as you increase. So once again, these are just like, it's almost similar to what we had with Fibonacci, just a different approach. With Fibonacci, we were doing the sum, whereas here we are trying to compute the maximum. So we're trying to get the maximum between two values. With Fibonacci, we are doing the sum of the previous two values. So almost very similar code. Like you could easily see the similarity between how we've written the code there, and you're able to get the result. So there goes the result. That's how we do the top-down approach, and you can see it works well for this standard test case. It also works well for this other test case where we actually had to skip two houses where the optimal should be 4 instead. In the next video, we'll now go ahead and look at how can we implement this with the bottom-up approach, which is what we'll recommend for most, if not all, of your dynamic programming problems.